Test, test, test. Okay, I can see the screen now. Test, test, test. All right. So it's almost time for our second meetup, which will introduce a modular robot survey. So if you are here, please type something in the chat window. I will wait for 1 to 2 minutes, and then we're going to start. All right, so I guess it's time to start. So welcome to our last webcast for the year, for 2016. I'm going to take a short break in December because I'm going to do some traveling, and then I will come back on January 2017, and hopefully we will rock it together in the new years. So today we are going to cover a number of modular robotic systems. So let's start. Before we start, I am going to announce our usual call for proposals because we need to hear from you. So please contact me directly if you would like to talk about projects, research, or just something cool you like to share. We need you, and we want to have you involved. So let's do it together. Our agenda for today will cover a small introduction. We will discuss modularity, and then we will cover some modular robotic systems. And finally, we're going to conclude. So, what are modular robotic systems? So modular robotic systems are composed of multiple building blocks of a relatively small repertoire with uniform docking interfaces that allow transfer of mechanical forces and moments, electrical power, and communication throughout the robot. The modular building blocks often consist of some primary structural actuated units and potentially some additional specialized units such as grippers, feet, wheels, cameras, payload, and energy storage and generation units. Modular robotics have become of great interest in the robotics community recently for a number of reasons, including economic mass production of units, graceful degradation of function when damaged, and the ability to transition into topologies suitable to the task at hand. In the modular systems, each module involves actuators, sensors, computational and communicational capabilities. Usually these systems are homogeneous, where all the modules are identical. However, they could be heterogeneous and contain different modules to maximize versatility. Modular robotic systems have 3 promises: versatility, robustness, and low cost. Versatility comes from the modular system's ability to form a large variety of shapes with large number of degrees of freedom. the robot might change its shape to suit different tasks and environments. The versatility of a modular system can be measured by the number of isomorphic configurations that system is capable of forming. For many systems, this number grows exponentially with the number of modules. Another measure can be the number of degrees of freedom in the system as it grows with the number of modules linearly. Let me say that again. Another measure can be the number of degrees of freedom in the system as it grows with the number of modules linearly. Robustness is the second promise. Comes from redundancy and self-repair, which ensures systems availability. And finally, low-cost promise is achieved through batch fabrication. As the numbers of repeated modules increases, the economies of scale come into play and the per module cost goes down. So let's start now discussing a number of different modular robotic systems. And let's start by CEBOT, which is one of the first modular robots that was developed in 1990 as a distributed intelligence system. CEBOT is a cellular dynamically reconfigurable robotic system that consists of units called cells. As you can see in the figure, on the right you can see the cells. Those cells can build up modules that can connect to other modules to form very complex systems. These cells can automatically communicate, attach, and detach to perform a function. And CEBOT is capable of dynamically self-reconfiguring to an optimal structure depending on the task and environment. Next, we have Polypot, which is composed of two different modules. You can see the two modules on the right. The segment provides 2 degrees of freedom, and the node supplies power to the segment. The segment is the one on the left, and the node is the prismatic look module on the right of the first figure, the one with the white background. Those segments can self-reconfigure to form different shapes and produce different locomotion methods, such as cartwheel. Sorry, excuse me. Allergy season, I'm sorry. Sneezes come and go. Okay, so the different locomotion gaits that Polypot can form includes cartwheel, slinky, rolling track, earthworm, and caterpillar. In the figure on the right with the black background, you can see, what is that? Tell me what you can see. What is it? It looks like a wheel. Well, they call it a rolling track. Huh, rolling track wheel. That's similar enough. All right, next. We have Metamorphosing Robot. Metamorphosing Robot is a dynamically reconfigurable unit modular robot. The mechatronic modules in this system can connect, disconnect by rolling over adjacent modules to allow autonomous self-reconfiguration. Each module is a planar hexagonal, as you can see in the figure. The hexagonal-shaped robot each has 3 degrees of freedom, with each side of the hexagon can connect to a side on another hexagon of the opposite polarity, positive and negative. Each module allows power and information to flow through itself and to its neighbors. As the number of modules in metamorphic system approaches infinity, the manipulator can be viewed as a mechatronic amoeba. similar to the amoebas in biology, because the manipulator takes on a continuous appearance. I think you can see the similarity in the figure, right? Alrighty, next we have Fractal. Fractal was designed in 1994 as a modular robot that is composed of homogeneous mechanical units. Each unit is called a fractum. The big robot is called a fractal, and the single unit is called a fractum. How cool is that? The fractum is considered as the atom of the machine. The figure on the left, again with the white background, shows a two-dimensional fractum. The fractal system is capable of self-assembly, since each unit can connect to other units autonomously to form a given shape through a diffusion-like process. The system is capable of self-repairing as well as an extension of self-assembly that can detect damage and let the whole system reconstructs itself accordingly. Fractal robot is shown on the right with the darker background. Next, we have molecules. Molecules were developed by Russ and her team in 1998. Molecules is a self-reconfigurable robot that supports various locomotion modalities by organizing autonomously as geometric structures to best fulfill the task in hand. Each module consists of two atoms connected by a right-angle rigid bond so that their relative orientation is 90 degrees, as you can see in the figure on the left. This time with a darker background. The one molecule has, which is the one module, has how many degrees of freedom? It has 4 degrees of freedom. 2 rotational degrees of freedom about the bond and 1 rotational degree of freedom per atom. And since we have 2 atoms, so we have 2. So the total is 4. These molecules can be aggregated to form 3D structure as the structure that you can see in the figure on the right with the lighter or with the white background. It looks like a planar tiling, right? Like a tile that is made using molecules. Meet up, search for name. Oh, hi, Stefan. There wasn't a URL. Oh, okay. I'm so sorry about that. I sent it in the email, and yeah, I forgot to update the meetup. Apologies. So give me 1 second. I will post the URL there. Thank you for the heads up. Thank you very much. You know, it's holidays time, and everyone is preparing to travel and to do a lot of things. Oh my God. Okay, so here is the URL. Save. All right. Thank you again, Stefan. I just updated the link. Yeah, I guess because many people, they don't receive the emails. So, my bad. But thanks again. Thanks. I really appreciate it. So you didn't miss a lot. And you can also go back and watch the video on YouTube. I didn't see it on my email either, but yeah, I don't know what's happening with Meetup emails lately. I'm missing a lot of their emails, like in the past couple of months. So we're gonna fix that. Yeah, right. Oh, thank you for your understanding. Appreciate it. So The beginning was introducing modular robotic systems, and then I went through some modular robotic systems, including CEBOT, Polypot. Now we're going to cover Polypot, which is not similar at all to Polypot, although the names are similar. All right. Okay. So Polypot, oh, I'm still stuck with the old name. Polypot is a modular, self-reconfigurable robot that was implemented in the year 2000 to explore how realistic it is to implement robots using several homogeneous hardware modules. As you can tell, all the modules or all the systems that we covered already are homogeneous. We didn't cover any heterogeneous system yet. These modular self-reconfigurable systems have three characteristics, which we mentioned as the promises of any modular robotic systems, which are versatility, robustness, and low cost. There are three generations of Polypot robots, generation 1, 2, and 3. And you can see each module of the three generations on the top row of the slide. The one on the left is the first generation, the one in the middle is the second generation, and the one on the right is the third generation. The first two generations of Polypot prove versatility very well by executing locomotion over a variety of terrain. However, as the number of modules increases, cost increases and robustness decreases due to software scalability and hardware dependency issues. Currently, the maximum number of modules utilized in one connected Polypot system is 32, with each module having 1 degree of freedom. The figure that you can see in the bottom row is a second generation Polypot robot. Then we have Crystalline. Crystalline is a distributed robotic system that was developed by Russ and Vona in 2001. This system consists of atoms having 3 DOF, degrees of freedom. Oh, cool! Stefan recognizes Polypot. There was a delay. I couldn't see the chat messages, and now they popped up at once, so I can see it. Okay, do you recognize Crystalline? It's a famous one, but not as famous as Polypot. Yeah or no? But to be honest with you, I heard of it before starting this research, the survey, but I heard it. Okay. All right. So each atom in Crystalline has 3 degrees of freedom, which allows expansion and contraction by a factor of 2, which similar to muscles functioning method. And you can see it in the figure. This is the crystalline, the atom, when it's contracted, and the figure on the right shows it when it's expanded. How cool is that? Yeah, it looks interesting, right? So robots are formed by expanding and contracting each atom frame in order to move relatively to the other atoms. These movements simulate muscle actuation mechanism, as I mentioned earlier, which permits automated shape metamorphosis. Crystalline robots are capable of self-reconfiguration very fast, in O of n squared time, where n is the power of atoms, so that's very fast, which is good. These robots carry a number of redundant modules on their bodies. Guess why? to allow self-repair that can be accomplished by ejecting the bad module and replacing it with one of the extra working modules. Next, we have Conroe. Conroe is a self-reconfigurable robot with inter-robot metamorphing capabilities, which allow the robot change of shape to result in creating new robots or merging existing ones. So a new robot is created when a large robot releases some of its modules for this purpose. That's similar to like ants deliveries, not ants delivery, like insects deliveries. I don't know. What do you guys think? I'll continue until you type. Two independent robots can also merge when they link their modules to create a single larger robot. The basic shape of a Conroe module is composed of 3 segments connected in a chain, as you can see in the figure on the left. Robotic modules are equipped with sensors in order to collect data and provide necessary feedback to guide self-reconfiguration locally on each module. A set of modules can be connected together to create complex robots, such as the ones you can see on the right. These looks like hexapods, right? Well, for me, it looks like hexapods. All right. Next, we have MTRAN. MTRAN stands for Modular Transformer. I love transformers, so that's why I love MTRAN. MTRAN is a distributed, lattice-based, self-reconfigurable system that is composed of homogeneous robotic modules. Stefan, if you're asking about MTRAN, it has 2 parts per module. Because Stefan has a question, 3 parts per module. If you are talking about Conroe, yes, each module is composed of 3 segments. You're absolutely right. And the 3 segments are connected in a chain. Yay, Stefan recognizes MTRAN. And Stefan also has another question about Conroe. This for the walker in that picture, 3 modules to make that. Yes, I guess it's 3 modules, probably 3 or more. I'm not sure about that, but I think it's, yeah, you're absolutely right. It's either 3 or more, 3 plus. Let's say 3 plus. Oh, no problem. Okay, so we will go back to MTRAN. Okay, so MTRAN has a special design for its modules. So each module is both reliable and allows quick self-reconfiguration. It also allows versatile robotic motion. Cool. MTRAN is capable to metamorphose into robotic configurations such as a legged machine that generates coordinated walking motion without any human intervention. The actual system that was built using 10 modules was examined through experiments to demonstrate the basic operations of self-reconfiguration and motion generation. So the basic module that consists of 2 segments is shown in the figure with the white background on the left. In order to drive MTRAN hardware, a series of software programs has been developed, including a kinematics simulator, a user interface to design appropriate configurations, and motion sequences for given tasks, and an automatic motion planner for a regular cluster of Mtran modules. These software programs are integrated into the Mtran system supervised by a host computer. I tried to look for these software online, but I couldn't find it. I appreciate if you guys can guide me, if you can find them or find a link to download them. So Stefan here is commenting on the design. I think he likes the design of Mtran. So Stefan is saying it's really a clever design, simplistic individual modules, but super flexible for larger configurations. I know that sounds weird when I read when I read the comments out loud, but I figured out after last time that all the questions and the comments are erased. So it was like, I don't know, it didn't look right when I was replying without reading the question or reading the comments. So from now on, I'm going to read everything. Okay, so Mtran, let's continue talking about Mtran. It has 3 generations, similar to Polypot, the one that we described earlier. In the second prototype of Mtran, various improvements were integrated in order to allow complicated reconfigurations and versatile whole-body motions. Those improvements contain reliable attachment-detachment mechanism, onboard multi-computers, high-speed inter-module communication system, low power consumption, and precise motor control. In the third prototype, Mtran 3, there was an improved connection mechanism with various control modes, including single master, globally synchronous control, and parallel asynchronous control. Well, I hope the same, Stefan. We had a common wish. I don't want to read it out loud. So the next is Unidrive Modular Robot. Unidrive Modular Robot was presented in 2003. I didn't find a lot of references about it. I found, I think, only 1 paper or maybe 2 papers, if I'm not mistaken. But it's still a good modular robot. That's why I included it in this presentation. So Unidrive has a new design for modular serial robot that is composed of lighter modules based on the Unidrive concept. So the main element of a Unidrive modular robot is a mechanical drive capable of providing a variable bidirectional speed from a constant unidirectional input velocity. The configuration of the new robot can be changed by the order and number of links and joints that make up each module. As you can see in both figures, the figure on the left shows a series configuration, while the one on the right shows a parallel configuration. Series versus parallel. So in order to reduce the module's weight in the new design, the actuator was replaced with a pair of clutches. That's interesting, because actuator often contributes a significant portion of the module weight. So next we have Tron. Tron stands for another modular self-reconfigurable robot. Is it, or am I mistaken? I think I'm mistaken. Yamor, actually, Yamor is yet another yet another modular robot. Yeah, no. It's not Tron. My bad. Tron is a lattice-based system consisting of approximately spherical modules, where each sphere or semi-sphere is constructed as two hemispheres joined by an infinite revolute joint, as you can see in the figure on the left with the white background. Actuation is realized as rotation around an axis diagonally through the sphere. This design allows for a very stable construction around the actuated joint, since a relatively large area is available for mechanics. I know, so many acronyms. The spherical basic module design makes it hard to have big flat surfaces connecting to each other. With spherical modules, connectors need to establish essential point-to-point contacts between modules, which is not desirable due to high collision probability. Despite that, Tron modules are minimalistic because they have only one actuated DOF, or degrees of freedom. The group of module is capable of self-reconfiguring in 3 dimensions. I like Tron. I think this modular robotic system can do a great job if offered commercially or somewhat. So next we have the lovely triangular programmable parts, which can be assorted on an air table by overhead oscillating fans to self-assemble various shapes according to the mathematics of graph grammars. That sounds very complicated, to be honest. The modules can communicate and selectively bond using mechanically driven magnets without global knowledge of the full shape. Despite planning to build approximately 100 parts, only 6 parts were built for design simplicity. Well, 6 out of 100, I don't find this convenience. I prefer if they built more. But however, those 6 parts were used in an experiment that showed these parts react similarly to chemical systems. Another researcher, Knapp, added measurements of kinetic rate data to the work previously done by the people who build programmable parts in order to yield a Markov process model. The parts do self-assembly and they build different shapes. The behavior is similar to chemical systems. About functionality, I don't recall reading something about their functionality. I don't remember reading such a thing. So the big reason for building these triangular programmable parts was to experiment self-assembly in a way similar to chemical systems. That's why also they use the air table with overhead fans. But that's a good question. Do the parts perform different functions? If anyone has a better answer, please share it with us. Roombot. Roombot is famous because everyone is crazy about furniture. Not everyone, some people love furniture. I'm not a big furniture person, but I heard of Roombot. So Roombot is a modular robot that can self-assemble and self-reconfigure into different pieces of furniture. It introduces passive elements in the robot structure, the implementation of a central pattern generator for generating the command of the motors, and the possibility of using a motor in oscillation and constant rotation. So the figure on the left shows the basic module of RoomBot, which also consists of two pieces or two segments. The figure on the right shows a table that is made up of RoomBot, various modules. I also saw a video, remembering seeing a video about RoomBot modules that connect together in order to make a chair. I found that very interesting. Yeah, Stefan added rearranging furniture for meeting rooms. Interesting. And also for the people who live in like small areas and studios, such as students like us, like grad students or researchers who unfortunately live in studios or small places or share our places with other people. That's going to be great. That's going to be a good idea. Having extra table for parties or extra chairs for the holiday season. That's going to be very useful. Oh, yeah. So, Samba. Samba looks scary. Samba is a mobile self-assembly modular bot that was implemented recently in 2010. Several modules can self-assemble to form a particular structure through a 4-phase autonomous docking process. The resulting shape can reconfigure into different structures that are capable of locomotion. Each module includes an active docking interface and an autonomous mobile body. A pair of detecting infrared sensors is installed on the autonomous mobile body to detect obstacles in front of the robot, which is really cool. Also, a pair of approaching infrared sensors is installed on the autonomous mobile body to monitor the relative positions of the modules and provide navigating information for the docking. The computing platform provided for each module is distributed and consists of a number of interlinked microcontrollers. The interaction and connectivity between different modules is achieved through infrared sensors and Zigbee wireless communication in discrete state. Long time I didn't hear about Zigbee wireless boards, but it's cool to see it in research projects such as Samba. Yeah, and the figure on the left shows a Samba module. The figure on the right shows a configuration of robotic structure. That's right, yeah. Stefan added that a Samba can configure for walking robots, similar to Tron. That's absolutely right. And I like about it that each module in Samba is different than the previous modules that we see, that each one of the modules is composed of 2 or more segments, but here in Samba, no, the module has only 1 segment. So I think that's a different factor, differentiation factor. Yeah, Stefan also uses Zigbee. I like it. It has great wireless capabilities, especially for robotics. They're absolutely right. M-blocks. M-blocks are different from cubelets, the one that I mentioned last time in our last meetup. They look a little bit alike, but they are different. M-blocks were introduced in 2013 as a cubic modular robotic system that is capable of self-assembly and self-reconfiguration. This robotic system cannot self-repair. Why? Due to the lack of intelligence incorporation into the system. The cube-shaped module uses pivoting motions to reconfigure and change geometry. The robot has three critical systems: the magnetic bonding and pivoting mechanism, the inertial actuator, and the electronic control system. The magnetic mechanism allows the modules to quickly form magnetic hinges on any of the cube's 12 edges. The inertial actuator is one-dimensional unidirectional actuator that is not strong enough to execute all lattice moves reliably. So the figure on the left shows two M blocks, neighboring M blocks, and the figure on the right shows a group of modules. There is a video on YouTube of these M blocks and how can they reconfigure by rolling over the other modules. It's a really cool video. I encourage you guys to go and see it. It's a really cool one. Well, they are not permanently attached at one edge, because on the figure on the right, let's talk about, for example, the white box on top. In the video that I saw on their website, this white box was rolling and moved from being on top of the orange box to be on top of the red box, and then it moved again to be on top of the black box. So I don't think they're permanently attached at one edge. They're always, but not, yeah, I understand what you're talking about. Stefan said it sounds like they are permanently touching at one edge, but not necessarily the same two blocks, because one block can move from one place to another, but a group of blocks must be attached or must be touching at one edge in order to at least communicate and share resources. No, you're good. You were good. I can't believe it. So we reached the conclusion. So in the paper that I wrote, it has more robotic systems that I covered. But this paper is in press right now. Once it's published, I'm going to share with you the link so you guys can read it and share with me your feedback, which I really appreciate. So let's conclude together. In this presentation, we have presented a comprehensive survey of modular robots that were created to meet three main goals, which are versatility, robustness, and low cost. Modularity offers a number of features that were used to differentiate types of modular robots from self-assembly to self-repair, of course, including self-reconfiguration and self-reproduction. Today, because of time concerns, I didn't compare the major systems or the major modular robotic systems. But in our first meeting, after the break, we are going to compare a number of these major modular robotic systems. So if you have any ideas, any suggestions, any resources that you would like to share, please feel free to contact us. So, any questions? Yay, I'm happy that Stefan recognized some of the systems from his past research. That's really cool. And please accept my apologies because I forgot to put the URL. I sent the email, but I forgot to update the meeting details. But mistakes happen. I need to be more careful next time. I think we don't have any questions. All right. Thank you very much, guys, for your listening and for your participation. I really appreciate it. Happy belated Thanksgiving. Happy holidays. And enjoy the cold weather and enjoy the holiday season. You're right, it's so easy to forget. You're gonna buy gifts, you're gonna prepare for traveling. Oh my god, it's crazy. But thank you very much, and enjoy the holidays, and enjoy the rest of your day and the rest of your week. Have a good one. Thank you very much. See you next year. Alrighty, excellent. Take care, guys.